Hello and welcome, class, to part 3 of chapter 16, where we are overall discussing equilibrium and reversible reactions. Today we are going to be getting into the spontaneity of reversible reactions. In other words, we're going to be tying together our second law of thermodynamics into the reversible reactions and their nature, both flowing forwards and backwards. So specifically, we'll be looking at if a reaction is just mixed, based off of initial conditions in comparison to what we know of the equilibrium conditions to be, how can we predict meaningfully in which direction the reaction will shift? Will it go predominantly forwards? Will it go backwards? Or coincidentally, are we already at equilibrium? All right, so there are a couple of different ways that we can predict spontaneity and what it means in a reversible reaction. So if we want to predict the direction of a reversible reaction, whatever direction it's going to spontaneously move in. So spontaneous, again, in this sense, means that the reaction requires no continuous energy input. So the reaction itself, you don't need to force it to move in any direction. It will spontaneously shift either from reactants to products, or in this case, also possibly from products to reactants, all on its own spontaneously. Okay, so there are two different ways that we can predict the spontaneous direction of a reaction. Either we can use this concept known as the reaction quotient, which we will be describing shortly, or we can use our good old Gibbs free energy as was described in chapter 14. We are going to be looking at a slightly modified version of Gibbs free energy, a version of Gibbs free energy that includes the equilibrium constant K. The main premise, though, like why we care about this, is that once your direction of the reaction is known, an equilibrium concentration for reactants and products can be found from initial conditions. So what we looked at last Friday was how do you find, an equilibrium concentration of X if you're at equilibrium, if you already know Kc. So we learned how these two pieces connect. Today we're going to be looking at, well, if you don't know the equilibrium conditions, if you just have a Kc from initial conditions, how can you predict what these equilibrium concentrations are going to be? All right, so our first concept is the reaction quotient. This is represented by a variable Q with a lowercase c, in this case also representing that we are working with concentrations. Now our concentrations, being or corresponding to the subscript of the C does imply that there's like a QP or other forms of the reaction quotient that mirror the equilibrium constant. We'll be working with QC most of the time. So this is the ratio of the products and the reactants concentrations for a reaction that is not yet at equilibrium. So the equation itself looks very similar to C, right? K. This whole reaction looks like Kc. We have products raised to the exponent of their stoichiometric coefficients, all divided by reactants raised to their stoichiometric coefficients. The major difference is that this calculation for Q is not at equilibrium, since the forward rate is not necessarily yet equal to the reverse rate in this reversible reaction, which is why in the expression for QC we have these little subscripts of I. These mean initial conditions. We are not at equilibrium. Initial conditions. All right, we are not at equilibrium. All right, but the magnitude of Q relative to K, right, that's what we're going to be looking at down here, points 1 through 3. This Q versus K can tell you something about the direction, though, of your reaction and which direction it's going to spontaneously move. All right, so first let's look at situation 1, where Q is less than K. If your Q is less than your K, in other words, if your initial conditions ratio of products to reactants is less than that at equilibrium, well, what this means is that in order for this value of Q, numerically speaking, if we're kind of comparing numbers, our Q is only going to be smaller than K if we have too many reactants, right? So if we have too many reactants, this means too many reactants. It means that your reaction must shift forward. Your reaction must shift from reactants, shift forward. It must shift from reactants to products in order to remove some of the reactants and also create some more product. All right, so just cleaning up the slide there a little bit. So in our first case scenario, this is, again, just to rewrite this for the sake of comparison, shifts forward. All right, so in our second situation that we're going to be looking at, what happens or what does it mean when your Q, your reaction quotient, is greater than K? Well, what this means is that initially, if your Q, again, in terms of number, in terms of magnitude, is too big, it must mean that you have too large of a numerator. Now, if you have too large of a numerator, this means that according to the natural balance of this reaction, you have too many products. All right, and if you have too many products, then the reaction must spontaneously shift in reverse. It must shift away from product, reverse. It must shift away from the product and more towards the reactant in order to balance this product to reactant ratio. Right, so in first situation, if your Q, represented again by initial conditions, is too small compared to your K, your reaction must shift forward. If your Q was too large, then your reaction must shift backward. So this is going to tell us then again which direction the reaction is going to shift in order to reach equilibrium, right? It's all about reaching equilibrium. There. This is what we're always trying to get to, or this is the state that we are trying to get to. Since reversible reactions don't, again, have like an end, you don't reach a point where you run out of reactants. Instead, what's going to be happening is the reaction is aspiring to reach equilibrium instead. This very steady state where your rate forward is equal to rate reverse. All right, the last case scenario then, scenario 3, if your Q is equal to K, well, again, this is sort of like a Goldilocks situation. If your Q is equal to K, you don't have too many reactants, you don't have too many products. In fact, you have reached equilibrium. Your forward rate is equal to your reverse rate, and there is going to be no shift. There, no shift. Okay, so our reaction quotient then is useful to us in that it tells us from initial conditions where we're going to be going in order to reach equilibrium. So the reaction quotient, this concept, can also be visualized. Right, we also had a similar visualization when describing equilibrium in the first place, this reaction where our N2O4 is decomposing into 2 nitrogen dioxides. There's going to be a point where your reactant, is going to be decreasing in concentration, your product increases in concentration, but then there's a point where your reaction is going to, if it's reversible, hit this nice equilibrium steady state. So concentrations can be monitored as time passes to observe this type of spontaneity. So for example, let's look at what the QC for this reaction is going to look like. And our QC is going to be calculated by looking at the concentration of our NO2 squared, all divided by the concentration of our N2O4. And these are going to be at some point of initial conditions. So initial, it's really important to recognize, initial does not necessarily mean T equal to 0. It's going to be anywhere along the spectrum right up until we hit where equilibrium is reached. So it's going to be important for us to define exactly what our initial conditions look like. So let's look at a couple of different points on this chart and see what the data is telling us. So the first point we'll look at will be, sure, T equal to 0. Why not? This is a really standard sort of T equal to 0. 0 seconds right at the beginning of the reaction. It's a very simple, straightforward, consistent way to measure initial conditions. So initially we have a 0.2 molar N2O4 solution, and we have none of the, we have 0.2 molar of the NO2, we have 0.2 molar of our product, and we have none of our reactant. So of course, if we don't have any reactant, well, it would stand to reason that the reaction is going to have to shift backwards in order to hit this. And this is exactly what our Q is telling us. Our Q at T equal to 0 is going to be, right, we have some concentration, 0.2 molar. We're going to square that, and we're going to divide by nothing. Well, if you divide by nothing, that means that your Q is going to be infinite, which is exactly what we see down here underneath the graph. And if your Q is infinite, this is definitely bigger than K, right? Regardless of what K could be, your equilibrium constant, infinity is bigger. It is infinitely bigger, which means that your reaction has too much product and must shift backwards in order to regenerate some of this reactant here. And that is exactly what we end up seeing, right? The concentration of your product goes down and the concentration of your reactant goes up. At some other point T in the future, we can try and double check, like, are we at equilibrium yet here? So this point is going to be when your concentration of reactant and product are both equal to 0.08 molar. And so again, one common misconception is that equilibrium means that your concentrations are equal. This is not necessarily going to be true. All right, so let me clean this up a little bit. All right, and we can rewrite real quick what our QC expression is going to be equal to. It is going to be concentration of products squared. So the concentration of our product is that 0.080 molar. We can square that. And this is going to be divided by a 0.080 molar. Now what ends up, or what Q ends up mathematically equaling is a 0.080. And for anyone who is keeping track, the equilibrium constant for this expression as it is written is 4.65 times 10 to the negative 3. So what this tells us is that, yes, even though we have equal concentration of product and reactant, we are not at equilibrium since our reaction quotient is still greater than our Kc, this 4.65 times 10 to the negative 3. So we are not at equilibrium yet. So if we let the reaction progress, again, what this is telling us is that we still have too much product. Our reaction is still going to be shifting back towards our reactant. And so as the time increases, we see that eventually we hit this steady state where, yes, in terms of concentration, we have more N2O4, but what's important is the ratio between the N2O4 and the NO2, and that we have more of the NO2, which is what we would naturally expect based on our equilibrium constant. This is the constraint that tells us what is the balance between reactants and products for this given reversible reaction. All right, so we've looked at the reaction quotient both conceptually in equation form and also visually through the graph that we just looked at. So here we have an example problem then, which I would love for you to pause the video and attempt quick just to look at the numbers then yourself, without a graph, just we have some initial conditions here. We are told that the previous reaction, which also is relisted here, is proceeding after 0.450 molar of NO2 is mixed with 0.004 molar N2O4. Again, the equilibrium constant is repeated here, so I would love for you guys to calculate this Q, compare it to K, and determine in which direction is this reaction going to proceed. All right, well, after, we're coming back together, in order for us to solve this problem, what we're first going to have to do is write out our expression to solve for Q. Now, the balanced chemical equation, again, is provided here, and we write out our Q in the exact same way as we write our K. The only difference is that the concentrations that we are listing are going to be initial concentrations, hence, again, the subscript of an I, instead of equilibrium conditions. We will still be looking at the ratio of product divided by reactant, and we'll be taking all of our stoichiometric coefficients and raising them into the exponent. So we have our equation for the reaction quotient Q here. All we need to do is plug in the concentrations that we have. So the concentration of our NO2 is 0.450 molar, and we're going to square this. And we will take it divided by the concentration of our N2O4, this 0.004 molar. Now if we calculate what our Q is equal to, we find a value that is equal to 50.63. And again, I'm being really loose with my significant figures here. So like we started with one value that has 3 significant figures, another value that has 1 significant figure. If we want to be really technical, this number should be represented as 5 times 10 to the 1, or in other words, 50. We could also rewrite it as 50 without the decimal point, signifying that we have 1 significant figure and that the 0 is not important. Either way you write it is fine by me. Again, we're at a point in the semester when there are so many things to keep track of. Some numbers have units, some don't have units, like our equilibrium constants and reaction quotients here. Significant figures are not something that I'm super concerned about at this point, so long as the answer is in the correct ballpark. So that's just something to keep in mind moving forward. I would encourage you to continue getting practice. Like, don't completely forget about what a significant figure is, but there are going to be other more important things to worry about at this point in the semester. All right, but the real question here is not what is the Q, but rather how does the Q compare to the K? How does the reaction quotient compare to the equilibrium constant? Well, we can see that the equilibrium constant of, the reaction quotient of 50 is definitely larger than the equilibrium constant of 0.0046, right? This is definitely, this Q is definitely larger. So if a Q is too big, our Q is too big, what this tells us is that the numerator must be too large and the denominator must be too small. In other words, we have too many products. And in order for this reaction to reach equilibrium, we're going to have to shift to the left in order for equilibrium to be reached. We're going to have to shift towards the reactant side in order to rebalance and reach equilibrium. Okay, so we can also use Gibbs free energy, as was previously stated, to determine what is the direction of our reversible reaction. So the reversible reaction that is not at equilibrium will spontaneously move towards equilibrium, which is what we have been talking about, according to what its Gibbs free energy is going to be equal to. And so here we have this new equation present. What this equation represents, we'll start our way from the right and move to the left. So we have a Q that is present inside of this natural log, which stands for the reaction quotient that we have been talking about. Reaction quotient. We have T for temperature. This has to be, as one would expect, in Kelvin. And we have our gas constant R. So this gas constant R, since we are working with an energetic form, right, Gibbs free energy, should be equal to the 8.314 joules per mole Kelvin version. Okay, and now here's where we can differentiate between these two Gibbs energies here. Now the Gibbs free energy that is on the right-hand side of this equation does represent our standard Gibbs. And this standard Gibbs is going to be at 25 degrees Celsius. This is not a STP kind of standard. This is a different standard temperature. This is the same standard temperature that all of the Appendix 2 data is in, so we can use the Appendix 2 data to calculate what is our standard Gibbs free energy at 25 degrees Celsius. Now this modification, this additional piece, this RT natural log Q, tells us what is the balance of reactant or product to reactant, what's that ratio, and what is the weight of it. That's what this RT stands for. And so the balance between our Gibbs free energy calculation and this Gibbs energy component on the right-hand side that we're kind of adding, this modifier based on initial conditions, will tell us this new Gibbs free energy that's not necessarily at standard conditions. The temperature that can go into T does not necessarily have to be at 25 degrees Celsius. This delta G naught does have to be at 25 degrees Celsius. So as temperature changes, as our initial concentrations change, this is going to give us a new meaning to our delta G. All right, so let's talk about what this new delta G then stands for, what it represents. All right, so the delta G, if our delta G, kind of scenario 1, is negative, what this means is that the reaction will be spontaneous in the forward direction. So the reaction will shift from reactants to products because the balance between the Gibbs free energy in the standard conditions here and the modified conditions, either a modified temperature or modified initial conditions, there is something that is out of whack, something out of balance, and so your reaction is going to have to shift in the forward direction to create some more products in order to balance out this Gibbs free energy. All right, so again, the delta G's that we are looking at here are the delta G's that we have calculated on the left-hand side of the equation. If your delta G is greater than 0, if it is positive, your reaction will still be spontaneous. It's just going to be in the reverse direction. You have too many products. You're looking at a situation where your products need to shift backwards into reactants. So we might even be able to predict that if we had calculated the Gibbs free energy for the example we just looked at, we would have found a positive Gibbs free energy, since we saw based on concentration balance, your reaction has to shift in reverse. Now, the magical situation where your delta G is equal to 0 corresponds to a situation where you are at equilibrium. Your product to reactant ratio is balanced, your temperature is balanced, it being the reaction, does not have to shift in any way. Your Gibbs free energy calculation is good. All right, so when this equation or these concepts are going to be useful to us, because you see that this new Gibbs free energy equation does have a reaction quotient in it, so you might be asking yourself, well, like, when would I want to use this instead of just looking at Q versus K, which is what we just talked about? Well, there are going to be situations where you don't know your equilibrium constant. You don't know K. So if you don't know K, but you do have the means to calculate this Gibbs free energy at standard conditions, you can now calculate the Gibbs free energy for your reversible reaction and use the value whether or not it is positive or negative or equal to 0 to tell you whether or not your reaction is going to be spontaneously progressing in a given direction, or if it is already at equilibrium. All right, so let's look at an example calculation here. So we have some information that has been provided to us, like our delta G naught, our standard conditions for delta G of reaction at 298 Kelvin is found to be 16 kilojoules per mole. It doesn't necessarily matter what the reaction is, but we know what its Gibbs free energy is equal to. So if your reaction quotient, your Q, balance of products to reactants, is found to be 0.012, is the reaction spontaneous or spontaneously continuing in the forward or the reverse direction? So since no other temperature is given to us, it is safe to assume that our T, our temperature, is also going to be at 298. So we're just looking with our current Q at standard conditions at this 25 degrees Celsius, is your reaction going to progress forward or backward? All right, so we can use the equation that we just learned. Our delta G of reaction is equal to a delta G naught of reaction plus RT natural log of Q. So the standard Gibbs free energy was given to us, this 16.0 kilojoules per mole. Our R, again, is given to us, this 8.314. Now I am going to shift this into kilojoules, so I'm going to tack on a times 10 to the negative third to make this equal to a kilojoule per mole Kelvin value. Temperature, we're going to say, is that 298 Kelvin. So kelvins are going to cancel out here. We can see kilojoules per mole are going to be working together. Not necessarily canceling out, but they will be giving us a final delta G that is consistently going to be in kilojoules. So again, always going to be wanting to look at our units here and make sure that everything is playing together nicely. Now Q, much like K, does not have a unit associated with it, since we are looking at a ratio of molarities, or a ratio, again, of whatever your concentration unit is. It's safe to assume that they're going to relatively cancel out. So this Q does not have any type of unit associated with it that we'd have to necessarily worry about whether or not it's going to like play with the rest of them. But here we have a way now to calculate what the Gibbs free energy is going to equal. So whether or not you want to, again, shift your Gibbs free energy value into joules to match your equilibrium constant here, or not equilibrium constant, your gas constant, your R, or if you want to shift your R to match your delta G, just so long as they're consistent, it should be fine. So if we perform this calculation then, taking 16 plus this entire R times T times natural log of Q term, we should find a value that is equal to 5.0 kilojoules per every mole. So what we're looking at here is that the Gibbs free energy that we just calculated is positive. It is greater than 0. So what this tells us is that our reaction is going to be spontaneous because it is not equal to 0. And it's going to be spontaneous in the reverse direction. This Gibbs free energy is positive, meaning that progressing in the forwards direction will only make the reaction less stable. A Gibbs free energy is going to, it represents like spontaneity in the forward direction. If it is negative, that's going to be consistent with the Gibbs free energy as we talked about it in chapter 14. So here it's going to be spontaneous, our reaction will be spontaneous, but spontaneous in reverse. All right, so let's say, again, because I had said that this version of Gibbs free energy equation is useful to us if we don't know K. Well, can we use this information to find K? What is the equilibrium constant for the hypothetical previous reaction? And we can use our equilibrium constant to determine also whether or not reactants, products, or kind of both are favored. In other words, like what's the balance of products to reactants as we had talked about on Friday. All right, so what's really cool about the previous equation, as we had talked about it, is that delta G of your reaction, not delta G standard, the delta G as it is calculated. If it is equal to 0, what this means is that you are at equilibrium. So if your delta G is equal to 0, well, you're at equilibrium, which means also that your Q is equal to K, right? If you're at equilibrium, both of these concepts were stated to be true, which means that in your Gibbs free energy equation, where your delta G is equal to 0, you have a delta G naught of reaction plus R times T times natural log of K, right? At equilibrium, Q is equal to K, which means we can plug K into this equation here, as we have also inserted 0 for our Gibbs free energy. And now we have a way to calculate K if we know what the Gibbs free energy at standard conditions and the temperature of the reaction is. And this is also going to be true for every reaction, not just this hypothetical case, since by definition, your delta G is equal to 0 at equilibrium, and also Q is equal to K at equilibrium. All right, so let's insert the data from our previous example. Let's see. So this time I'm going to work through in joules. So we have a 1.6 times 10 to the 4th joules per mole, just so we can see how like both versions of this kind of work out. But again, just so long as your units are consistent, doesn't really matter. Your R is going to be 8.314 joules per mole Kelvin. Temperature, we're going to assume that we haven't changed it since the temperature was not stated to change. And last but not least, we have a natural log. Wow, that's a bad N. Natural log of K. And all of this is going to be equal to 0. So now we have a way to algebraically rearrange and solve for what K is going to be equal to. I leave this algebraic exercise to the viewer since you're going to have to be able to perform these algebraic calculations on your own, but I will give you the final answer just so you can compare or have something to compare to. Your K, your equilibrium constant, is going to be equal to 0.00157. Now this value is definitely less than 1. This represents then, this equilibrium constant represents a ratio of products to reactants where products are not being very heavily favored. Your reactants are being heavily favored. Since this is less than 1, it means that in your equilibrium expression, you must have a very large denominator, and your denominator is where the concentrations of your reactants can be found. And that is going to conclude our lesson for the day. So not too many new topics to introduce, but again, we're just focused here on laying the foundation to make sure that we have the tools that we need to understand equilibrium conditions and reversible reactions, whether we be starting from initial conditions, understanding which direction the reaction has to shift, or if we are at equilibrium conditions already. So here we have some example problems from chapter 16, focusing then on being able to determine the spontaneity of a reversible reaction, which direction our equilibrium is going to have to shift, or rather the reaction is going to shift to get to equilibrium. As always, though, if you have questions, please do not hesitate to ask the questions that you might have. If you have homework, please double check and do your homework. And until next time, class is dismissed.